An algorithm known as a priori is a common one in data mining. It is used to identify the most frequently occurring elements and meaningful associations in a dataset. As an example, products brought in by consumers to a shop may all be used as an input in the system. A priori is a seminal algorithm proposed by R. Agarwal and R. Srikanth in 1994 for mining frequent item sets for Boolean association rules. The name of the algorithm is based on the fact that the algorithm uses prior knowledge of frequent item sets properties. A priori employs an iterative approach known as a level-wise search where k item sets are used to explore k plus 1 item sets. First, the set of frequent one item set is found by scanning the database to accumulate the count for each item and collecting those items that satisfy minimum support. The resulting set is denoted L1. Next, L1 is used to find L2, the set of frequent two items sets, which is used to find L3, and so on until no more frequent k item sets can be found. The finding length of each LK requires one full scan of the database. The two-step process is followed in a priori consisting of join and prune actions. Here, finding frequent item sets using a candidate generation, and the algorithm uses prior knowledge of frequent item set properties and employs an iterative approach known as a level-wise search. K item sets are used to explore k plus 1 item sets. A priori property used to reduce the search space, and the a priori property is all non-empty subsets of a frequent item set must also be frequent. If a set cannot pass a test, all of its supersets will fail the same test as well. Here, a priori algorithms it follows two steps of actions, that is join step and prune step. Like in a join step to find LK, a set of candidates k items is generated by joining LK minus 1 with itself. This set of candidate is denoted CK. And a prune step consists of CK is superset of LK, that is its members may or may not be frequent, but all of the frequent k item sets are included in CK. A scan of the database to be determined the count of each candidate in CK would result in the determination of LK. To reduce the size of CK, a priori property is used, that is any k minus item sets that is not frequent cannot be a subset of frequent k item sets. Here, if we are going to be consider an example, so here the transactional data for a retail shop, and we need to find the frequent item set using a priori algorithm. There are 8 transactions in the database, that is D, the length of D is 8. And here in iteration 1, so generating candidate items set, that is C1, or candidate 1 item set, we can call that. And suppose that the minimum support count is required is 3, that is minimum support is 3, or relative support, that is 3 by 8 is equals to, we can call that is 3 is the like minimum required frequency of items, and 8 is the total number of transactions in a given data set, which is nothing but it is 37.5 is the minimum support, relative support. And C1, when we are going to be write all the distinct items, and if we are going to find their how many or their frequency in the given data set, then we are able to calculate that. Here we are having which consisting of, so this is frequent, here the frequent items that they are having these distinct items they are having so the support is like this. Here milk is repeated 6 times, and eggs are repeated 4 times, bread is repeated 7 times, butter 4 times, cheese 3 times. And here the minimum support count is 3. So that's showing these all are satisfied. And this CK1, so this is a C1, that is a candidate one item set is being labeled it as L1. Okay, here the frequent one item set L. Whatever that which are satisfied the minimum support count, they are labeled as L1. Okay, so with that the frequent item set L1 can be then determined. Here in a prune step, if any of these items, if they are not satisfying a minimum support count, then we are going to be removed. That particular items or item sets are going to be removed. But here the all the distinct items, these 5 items, they are satisfied the minimum support count. Now here we are going to move to the iteration 2. So that is join step. So this list 1 self joining itself, we are going to generate a candidate 2 item set, that is C2. So whenever it is going to be like when we are going to be considered, here we are having this milk is going to be joined with eggs, and then milk is going to be joined with this bread, and then milk is going to be joined with this butter, then milk is going to be joined with this cheese. It is going to be get a list of candidate 2 item set, and then further here we are having a this eggs is going to be joined with bread, and eggs are going to be joined with butter, eggs are these are going to be joined with this cheese. So like that, here we are having a, when we are going to be consider, we are able to get the C2 item set, that is like this milk is eggs and milk with butter, milk with bread, milk with butter, milk with cheese. And then again these the item sets. This is a pair of items. How many times they are being repeated, that we are going to be so list out as a support count, and which that they are not satisfying the minimum support count, that is 3. Then we are going to be prune. We are going to be remove. And here we are having a, so these are the items, okay, which that they are not satisfying. So this is 2, and here we are having 2, and here we are having 2, so that is eggs and butter, and here we are having 1, and here finally this butter and cheese is the frequency of these things are 1. So these combination of items that they are not satisfying the minimum support count. So that's why we are going to be prune these particular items, and by which whatever the uh, items that they left, then we are going to label it as list 2, L2. So here whatever these eggs and milk with eggs, their support count is 2, milk with cheese their support is 2, eggs with butter support is 2, eggs with cheese, somebody is 1. So these that they are not satisfying the minimum support count, which is 3. Okay. Hence, we are going to be perform the prune action, and whatever the items they left, then we are going to be treat as L2. Okay, here we got L2, which consisting of so all the items, combination of items or set of items, which that they are satisfying the minimum support count. So this we are now, this is being labeled as L2, and L2 is being derived from the candidate 2 item set, which satisfies the minimum support. And next iterative 3, L2 is being self-joined itself to generate the candidate item set 3. So here we got, this is the candidate item set 3, and here again we are going to perform the like the support frequency of these items in a data set. Then we are going to be identified and which that they are not satisfying the minimum support count, whatever that they are not satisfying. Then we are going to be like a prune. We are going to be perform prune action, and whatever the uh, from this candidate 3 item set. Okay, the items which are satisfied the minimum support count, so those items we are going to be labeled as L3. So that is list 3. Okay, here chain stop L over L2, L2 over L2 is being performed. Then whatever the generated candidate item sets, then we are label it as 3, and then we are examined how many of them that they are satisfying the minimum support count, and so then we are going to be we are going to apply prune action, and whatever that item set, okay, which satisfied the minimum support count, so that item set we are labeled as L3. And here we are having, then we are going to be generate association rule. So from these frequent item sets. So to generate strong association rule from this item set, we need to be calculate. So this confidence of rule, confidence. So that is confidence is nothing but here we know the formula. Confidence A tends to B is support count of A and B together over the support count of A alone. Based on this association rule, rules can be generated, and here for the frequent items set L, generally all non-empty sets of L, and here it is going to be satisfy the minimum confidence, and here this whatever the items that they are being calculated here, example contains the frequent items set L is milk, bread, butter, and among that, okay, what are the item sets that they are satisfying the like association rule can be calculated by computing this confidence over those particular one. So here, when we are going to be consider the milk, bread, butter item set, okay, among the given transactions, the confidence can be calculated. So milk, bread, butter together they appears in 3 items over the milk and bread that they are going to be appear in 5 items. So that's why here we are able to among this is 60%. So here we are able to conclude that the person who is going to be purchase milk bread, there is a 60% possibility of purchasing the butter. And when we are going to be consider milk butter bread, okay, here first of all we are going to be consider the all these 3 items together in how many transactions it exists. That if you are going to be count, there it exists in 3 transactions, and then we are going to be count. So in overall transactions, milk and butter together in how many transactions they purchased. And here this milk and butter it is going to be exist in 3 transactions. So here the confidence is 3 by 3. Then it is going to become, so there is a possibility those who are going to be purchased milk, bread, milk and butter, there is 100% like chance to purchase bread. And here we are having similarly we are able to calculate over the combination of items bread, butter, milk. Okay, so where there is we are getting the confidence percentage is absolute confidence is 75%, and milk, bread, butter. So by those who are going to be purchase milk, okay, so there is a 50% possibility or 50% chance of purchasing bread and butter. Like this, we are able to calculate. Okay, by applying the association rules, we are able to calculate what is the like probability of purchasing the other combination of items along with the proposed or the with this frequently purchased item. We are able to calculate. Here it is, and the minimum support, minimum confidence is 60%. So that's why, as whatever the confidence we have calculated, whether it is a strong rule or not to qualify that particular one. So the minimum required confidence is 60%. Among these fourth and fifth calculation, so fourth rule and fifth rule that they are not satisfying the minimum support, minimum confidence threshold is not satisfied in that. So that's why they are being excluded. That rule is not applicable. And here, this is one more example. Okay, where we are able to calculate in the same manner, and the total number of transactions in this particular data set are 10. That is D is equals to 10, and the minimum support threshold is 30%, and the minimum confidence threshold is 65%. Here, like that, we are able to calculate, and we are able to evaluate what is the possibility of purchasing other items by observing its previous transactions, and currently what customer is being opted, and what is going to be what further which kind of item sets that he may opt, we are able to calculate. And here we need to, there we are having some kind of limitations with this normal traditional a priori, and those can be, okay, those limitations can be overcome by applying these different techniques. That is, one is a hash-based technique, and another one is a transaction reduction procedure, and here partitioning of given data set, and another method is dynamic item counting, and so one more thing is the sampling method. So these are the different methods where we are able to increase the performance of the a priori algorithm. Here, if you are going to consider the hash-based technique, okay, so it can be used to reduce the size of the candidate k item sets, that is ck for every k greater than 1. Okay, such a hash-based techniques may be subsequently reduce the number of candidate k item sets examined, especially when k is equals to 2. In second iteration, the generation of candidate 2 item sets, every combination of 2 items, map them on different buckets of hash table structure, and increment the bucket count. If the count of the bucket is less than the minimum support count, then it is being pruned from the candidate set itself. So this procedure is going to be reduce the cost of generation of candidate item sets, and scanning these candidate item sets every time in every iteration scanning these candidate item sets throughout these particular database data sets. Here, when we are going to be consider this hash based technique, here we are having the given transaction data set consisting of 9 transactions, and here we are going to we were being given this minimum support code, that is 3, and the distinct items from the data set are, so this is A B C D E, and we know the minimum support code of, like, minimum occurrence of these items in the given data set is being written, and along with this we are also being written we are also writing, so we are giving some kind of order for these particular items. Here order of items are, okay, so here we are writing, so some kind of order for these particular items. Here it is A is equals to 1, B is equals to 2, C is equals to 3, D is equals to 4, and E is equals to 5. Here we are going to be compute this hash function over x and y. Okay, the hash formula is so that is order of x. Whatever the item here we are going to be take, so its order which is being predefined, like we were being given. So order of x into, so this is 10 items. For example, if you are going to be count 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 combinations, we are able to get these combinations. So that is order of x into 10 plus order of y. Here this particular second items order we are going to be write, and among this particular one, here the maximum frequency is 7, and we are performing a mod operation with this particular 7. By this we are able to get this particular hash values. Okay, so by generating this A to B, okay, this of count is 4, and A to C, and its corresponding hash value we are going to get, and this hash value we are going to be make use in the address for the buckets, hash buckets, and so like this for each and every combination of items we are being written the count as well as hash function is being computed. Okay, next. Here this according to hash function, hash values, whatever the hash values that we are being calculated by taking this particular one, okay, we are going to be, so place in that particular concerned bucket. So bucket address based upon this 0, okay, here we are having these hash values are consisting as a 0 value for this AD and CE set. So here in this first bucket address we are placing 2 items, and the bucket count is 2, and so this whether we are able to generate hash tables, so to generate the structure. Here we are it is the bucket count is 2, which is not satisfying the minimum support count. Okay, now here we are having 1. Okay, this 1 is going to be written here 1. AE 2 times it is repeating. That's why combination of 2 we are being written, and in the bucket address 1 we are having a, so these are 2 items, that is a 2 combination of items. So bucket contents are 2. So that's why here we are being written, and this is also not satisfying minimum support count. That's why it is not going to be qualified to go to item set L2. Okay, next, so this 2, when we are going to write this bucket address 2, in this we are able to keep the item BC. So BC consisting once, and here BC consisting twice, thrice, and 4th time. So that's why 4 items, 4 times the BC combination exists. So that's why its bucket count is 4, and similarly so on. If you are going to write these values which are satisfying the minimum support count, then we are going to be qualified. and the remaining items are being pruned, and we are going to remove them, which that they are not satisfying. Okay, minimum support count, and here we are having this one, two, and three items. Okay, which they are going to be like written in the L2. Okay, based upon this, without generating a like next candidate item sets, we are going to be qualify. We are going to be like generate the next list of items, and then we are going to be apply association rules over this combination of items, and if they are satisfying minimum confidence threshold, so those rules are strong and those rules are going to be adopted. So like this, we are able to improve based upon this hash measure function. And here we are having a, so another method is transaction reduction. Okay, so a transaction that does not contain any frequent item sets. Okay, cannot contain any frequent KPIs for the item sets also. That's why here we are going to be like identify such kind of transactions, and then we are going to remove them. So for further, we are not going to be consider them. Here, the minimum support count is being given to, and here these are the four item sets transactions, and here we are having a, and we are going to be like mark these transactions. So this item wise and transaction wise, if you are going to identify the item E is not satisfying the minimum support count, hence we marked it and we removed it. So further, we are going to be like the combination of items, and again the combination of items transaction wise and item set wise, whatever that they are not supporting minimum support count, then we are going to be marked and we are going to be removed. So on like that, we are able to get the finalized item, okay, which has to be considered to apply the like these association rules.